If you watch the collision videos that I posted on Schoology in our Schoology folder, there's a video of a marble being shot at a block, or there's also one where it's being shot at a soda can. And what ends up happening is that, here's the scenario here. There's our block, and you actually may notice, and I'll probably tell you to go back and look at the video a little bit more closely, but the block has a marking here showing you where its center of mass is on the video. And they send the marble in, and what ends up happening is that it comes in like this with a velocity v, and then it's going to impact at the bottom. Now, if the marble can do a few things, let's call this v1. All right, so at the point of impact, it's got a velocity v1 right here. It could rebound off, it can go through. I think in the video it rebounds off. Here we'll say it goes through, just to make it a little bit more simple from an introductory standpoint. What you see is that the block, upon the collision, the block moves to the right, also rotates. So this thing that's moving linearly is going to cause rotation here. And we're going to be able to analyze this. So let's have the block start to rotate like this. And what you're going to notice, and this is why that point's labeled there, is because it rotates around the center of mass. And then what's happening is that, obviously this marble here, it's affected. We'll have it moving at a slower speed afterwards. This thing's now rotating at omega. We see that the marble, which moves linearly, causes rotation here. Now, from an angular momentum perspective, we can analyze this. And a lot of people look at this and they're like, well, I don't see any angular momentum here because that thing's moving linearly. I think if you guys take Physics C, you're going to end up investigating this topic a lot more as to why objects that move linear have angular momentum. But don't get too hung up on that, because we just did a planetary body that was moving linearly, right? It's orbiting around the Earth, and at any given point in time, its velocity may be tangent to the circular path here. Let's think of it in terms of this. Looking at this marble here, where it impacts, we can see why this is going to rotate counterclockwise. The other video clips I posted, you see it actually impacting the top, and it rotates clockwise. So this marble is going to have angular momentum at this point in time here. And basically what you have to think about is, what does circular motion look like? If you're looking at something that's moving in a circle, if it's doing this or this, that's the equivalent to counterclockwise rotation. And, it's moving linearly to the right at this point in time. It's moving linearly to the left at this point in time. So what ends up happening is that if you took a marble and you shot it and hit it right there, it would cause the same rotation. So this thing, we're going to look at it immediately at the point of impact and say that this will have the equivalent of counterclockwise angular momentum. And we can express it in linear terms just like we did for the planet Earth going around the sun. So initially, this marble has all the angular momentum, and the marble's angular momentum would be equal to, well, before impact, immediately before the point of impact, it would be equal to m times v1 times r. Now we got to think about what r is. It rotates around the dot here, the center of mass. So this value right here is going to be r, halfway up the block. Now what ends up happening is that after, this was before, after impact, its velocity's got to be less here. So I'm going to say that L is going to be equal to mv2r immediately after impact. And what's going to happen here is that now this thing is rotating here. So if we look at the block itself, what we're going to get is that, obviously the angular momentum before is 0. It's not doing anything. But after, it's simply going to be equal to I omega, where I is the moment of inertia of the block. All right, so it's rotating about its center. We've got our before things, we've got our after things. Let's look at this from a collision standpoint. Now, one thing I have to point out to you is that you can look at the linear momentum, and you can do a linear momentum calculation of m1 v1i plus m2 v2i equals m1 v1f plus m2 v2f, just like we did in the momentum chapter. But we're also looking at the angular momentum aspect of these things. In this collision, both linear momentum and angular momentum are conserved. Let's focus on the angular momentum here. Before, you only have the marble having angular momentum. So the angular momentum of the system is mv1r, where m is the mass of the marble. Let's call this big M, because the block would obviously be heavier than the marble. And then what we want to do is look at the angular momentum immediately after the collision. It's got a different value of v, and it would still be located right here at the point of impact immediately after, so it's still going to be r away. So we're going to say mv2r. Now this is why I chose it to go through as opposed to rebound, because I want both my terms here to be positive for the sake of simplicity. We can look at that in another example. But now this thing's rotating as well. So we can write I omega here, but let's think about what I is. This is a block, and it's basically mostly in this dimension here. So we can use the thin rod moment of inertia equation in order to get that. It's rotating about its center. So the last thing I would do here is you could write this as 1/12. Its mass is m. The length is L here. So we could write L squared, and then we can write omega. And then one other thing you can actually recognize here is that L is equal to 2r in this case, so you could actually do some substitution in there and maybe get a little bit more specific here. But nevertheless, this expression here demonstrates your conservation of angular momentum. All right, so now that being said, let's just do the opposite example, one where maybe rebounds, because what ends up happening is that the expression changes just a little bit here, and that's what we saw in the video. Was we saw a rebound. I think when it hit the bottom. So we have a very, very similar picture here. In fact, the initial conditions look almost identical. It's coming in, and it's going to impact right there. The center of the block is clearly right here. And it's still a distance r away. But then afterwards, you get this thing flying back this way. And this thing is going to start to rotate like this. So you still get the same rotation, but you get this thing rebounding. And so initially, the angular momentum is going to be mv1r. That's not going to change, but the conditions afterwards change. And this would be equivalent to, let's take a look at just what if you just shot the marble this way. Its velocity would be to the left, and this would be its point of impact. It'd be just like that. This is going to be the equivalent of clockwise rotation. And if you think about an object moving in a circle, take a look. That's clockwise. That's clockwise. That's negative. So we would represent that here with a negative sign. The angular momentum is completely reverse direction for this object here. And then this would still be I omega. And then we can do the same substitution in there as well. So between this example and this example, the only thing that's different is now you have a negative sign here. Might result in a different value of omega based on that fact. But in both cases, we've demonstrated that angular momentum is conserved. Now, if you think about the soda can video, what you see is that the marble goes through the soda can, but it impacts it at the top. So why don't we do an example like that? You got the soda can here, and the marble comes in at the top with V1 here, and then afterwards the soda can's rotating this way, and it's not going as fast. It's V2, and this thing's rotating clockwise instead of counterclockwise. We'll take a look at our velocity. Now it's impacting at the top. This is the equivalent of negative angular momentum, clockwise rotation. So in my initial momentum expression, my initial angular momentum expression, I'm going to put a negative sign because that's going to cause negative angular momentum here. We'll make this little m here, this big M again. And then afterwards, it's still got the equivalent of that velocity there. So right, negative m v2r. There's the angular momentum before, there's the angular momentum after our marble. And then what we would get is a negative value when we solve for omega here. because this thing would end up rotating clockwise. Now, if this happened to rebound, that would end up being positive. So you got to kind of look at these pictures and figure out how to represent things with sine in this case. And this is probably one of the most challenging aspects, I think, of this unit here.